And welcome to my third part of the Git presentation. Today we're going to be talking about managing workflows to build a development narrative. And we're going to be leveraging Git to do this. There are two previous videos you can find on YouTube if you'd like to watch that. But anybody with any experience with Git, as long as you know the basics of commit and add, then you can easily follow along. So before we dive into the details of Git and what we're going to do today, we're going to take a moment just to explore the motivation behind what we're doing and why we do approach Git the way we do. So when we commit code, we're not just saving changes, we're telling a story about the code's journey. Each commit should capture a meaningful chunk of work, ideally focused on one task or feature. By doing this, Git becomes more than just a storage tool. It becomes a narrative of our development journey. These mindful commits are key to making Git a powerful tool, both in collaborating with the team and on your own. So a good rule of thumb with Git is to make each commit a single, motivated, self-contained, and meaningful change. So every commit should represent one logical step to your overall goal. So you would have an initial commit, oftentimes a node where you start your repository. You can add a feature if it has a related README with it, possibly fixing a bug. But if you're fixing two unrelated bugs, each fix should have its own commit. Combining multiple bug fixes into one commit makes it harder to understand the history and roll back individual changes if needed. Keeping the changes separate makes your Git history clearer and easier to manage. So for example, it's best to update your README in a separate commit from the feature yourself. This way you keep the feature code and the documentation distinct, making it easier to track changes and review each part independently. But as we'll be showing you later on, you can always combine these changes together when you have a better idea of the development story you want to tell. So when in doubt, commit early, commit often. So if you're refactoring a function, in our instance, if you're refactoring a function and you add a feature, and then you add another feature, you want to put all these things in their separate commits. So we're going to start, the first tip we're going to work on or to talk about is Git Stash. And Git Stash is a great tool for keeping your repository clean and organized. It's especially useful when you're in the middle of a task and you need to switch to something else or save your changes temporarily without committing them. So there's a few situations you'll find yourself in when you could use Git Stash. If you're working on one branch and you need to check out another branch, but you don't want to commit your changes quite yet, Git Stash lets you save your changes temporarily. It keeps your commits focused. When you have an unfinished or experimental work, stashing helps you avoid cluttering your commit history with half-done or exploratory work. And if you need to fix a bug in another branch, but you're working on something and you don't want to lose your current changes, stashing will let you push those changes or to save them without committing. So as we review from previous webinars and previous Git tutorials, there are three places in Git where file changes can reside. The first is the working directory, the staging area, and the repository. When you first check out a Git repo or switch to a branch, the working directory matches the staging area, which matches the local repository, and they're all in sync, reflecting the same content. And this means that initially, there are no changes in the working directory that need to be staged or committed, and your working copy matches exactly what's in the repository. When you edit a file, the working directory no longer matches the staging area, and this means that the file in your local workspace has changes that you haven't staged for commit. Git recognizes that your working directory has modifications, and you'll need to use git add to move these changes to the staging area if you want to prepare them for a future commit. Until you do, the staging area and repository will remain unchanged, reflecting the last committed state of the file. Git add. This step is crucial because it lets you decide exactly what to include in the next commit. By staging changes, you can review and confirm what has been saved, allowing for more organized and intentional commits. The stage changes will stay in the staging area until you run a git commit, at which point they're recorded permanently to repository history. And each commit creates a snapshot of your files at that moment, allowing you to track your progress, revert to previous states, and share work with others. Once committed, these changes are safely stored in the repository and can be synced with remotes if you're collaborating. So moving in the opposite direction, git checkout copies changes from the repository to the working directory. And this command allows you to switch branches or restore files to match a specific commit, making the repository's stored state viable and editable in your working directory. And it's particularly useful for navigating between branches or reverting changes in individual files without affecting other parts of your project. Now, git checkout is generally a safe operation. If you have unsaved changes in your working directory, git will prevent the checkout, aborting the operation and prompting you to address the changes first. This helps you avoid accidentally overwriting your work, giving you a chance to either commit, stash, or discard these changes before switching branches or restoring files. Alternately, you can use git with the reset -hard flag to overwrite any changes in your working directory. This command forcefully resets your working directory and staging area to match the latest commit in the repository. Now, be cautious, as any uncommitted changes will be permanently lost when using this option. So we want to remedy this, and there are many situations where you have code in your working directory that you want to keep, but you also need to work with code in the repository. So oftentimes this happens if you're developing an experimental feature or you need to handle a quick bug fix. In either case, you don't want to lose the changes you're working on, but they're not necessarily in a state where your code's going to run properly. So in the early days of Git, what you would have to do is you'd have to move these changes to their own branch before working on the code in the repository. But now we have git stash to simplify this process. When you perform a git stash, your changes aren't added to the repository or the staging area. Instead, Git temporarily saves them in a separate, hidden area outside of your regular commit history. These stash changes don't get pushed to your repository, so they aren't shared with collaborators. However, because they're kept separate, stash changes remain untouched by operations like git checkout or git reset, allowing you to switch branches or make updates without losing your saved work. So now you can git reset hard and everything's fine. Your changes are no longer in the working directory. And of course, once you're done with the edits, they're committed. You can use git stash pop to restore your working directory to its previous state. This command will replay your stash changes to the working directory, allowing you to continue where you left off. Now we're going to talk about the second tip for managing your workflow. We're going to talk about two operations, merge and rebase. And first, I just kind of want to set up the scenario that you'd be working in. Say you're working on a large, complex project, either with yourself or with multiple other team members, tackling different features at the same time. So you'd be switching back and forth, work on one thing, maybe fix something else. But when you finish with a feature with multiple commits on a branch, and it's time to integrate it with the main project, now you're faced with a choice. You have to bring these updates together without losing track of everything that was done. And this is where merge and rebase come into play. These are two different tools for combining work, each with its own philosophy. Merging keeps a snapshot of the contributor's progress, while rebase creates a clean, streamlined history as if everyone's work has happened one after the other. Both tools get you to the same place, but the journey is a little different. Now we're going to dive into how these two approaches work together and when you choose one and when you choose the other. So let's say we're working on a new feature. My repo only has one branch, the main branch. So we'll begin by creating a separate branch to make changes without disrupting the main project. We use git checkout -b feature. The CO is an alias, a common alias for checkout. And -b on checkout means create the feature branch if it doesn't already exist. So I've created a new branch called feature and switched to it. And now I'm free to develop on this feature branch without affecting anything on my main branch. Next, I'll create the new file feature.py and add it to the main branch and commit it, calling it, we've added this awesome feature. Now that I've committed this change, this is like taking a snapshot of my work. So now I can always return to it later if I need to. Now let's assume that there's an unrelated bug. I'll have to switch back to the main branch, modify main.py to fix the bug, and then add and commit to fix. At this point, the main and feature branches have diverged. And once the feature is complete, we'll need to bring them back together. And to do this, we'll use merge. So keeping a note here, we've added files and changes to the feature branch, and we've also added files and changes to the main branch that are separate. Now that we're done working on the feature branch, we merge it back in. So first we check out the main branch, which is the target branch, and then we merge the feature branch into main, into your checked out branch with git merge feature. Merge the feature being the name of the branch. These commands combine the two branches so that they now have share the same content. Note that the feature branch still exists, so you can continue working on it if you need to, but because we've merged the feature into main, main contains the changes from feature, but feature doesn't contain the changes from main. We take a look at the git log, we can see that git created a separate merge node that merged the main branch pointer to it. So the feature branch pointer remains unchanged. It still points at its original head, but there's a new node here for the merge node. Branching allows multiple people to work on different features or fixes simultaneously without stepping on each other's toes. Merging then lets us integrate all this work back in smoothly, bringing everything together. This workflow is essential in larger projects where multiple developers contribute in parallel. So this is known as a three-way merge because it considers 3 points: the head branch of the feature, the head of the main, and their common ancestor, where they diverged. And it's common to integrate changes from a feature branch into the main branch, especially when both branches have had independent updates. In other words, it combines changes from both branches, resolving any conflicts that arise. Now, this process is essential in collaborative projects, ensuring updates from multiple developers are unified and conflicts are minimized. When branches have conflicting changes, different modifications on the same lines, Git will flag these conflicts for manual resolution, which becomes your problem to do stepwise. And once these are resolved, the main branch reflects the combined work. Now, this is a slightly different merge scenario. So in this scenario, let's assume we don't make any changes to the main branch after creating the feature branch. So we've diverged from main and we haven't added anything to it. We've only added things to the feature branch. And as opposed to a three-way merge, if nothing has been added to the main branch since the feature branch diverged, Git will perform what's known or called a fast forward merge. You will note the output says, perform the merge, check out main, perform the merge, and you'll note that the output says fast forward, indicating what type of merge took place. In a fast forward merge, since there's no new work on the main branch, Git simply moves the main branch pointer forward to the latest commit in the feature branch. This fast forward the main branch to the same point as the feature branch, making it appear as if it was just a single straight line of development. There's no need to merge anything. There's no need for a merge commit node at this point because Git doesn't have to reconcile any changes from the two branches. It's just updating the branch pointer to match the main pointer. You don't always need to fast forward when a feature branch and a main branch haven't diverged. Sometimes it's beneficial to keep the feature branch separate, allowing you to monitor the changes more clearly and continue development independently. Here we see two different merge strategies. On the left is a fast forward merge, the default when the feature branch hasn't diverged from the main branch. And on the right is our three-way merge, which, unlike the fast forward merge, moves the main branch pointer forward directly to the feature branch's latest commit. The three-way merge creates a new commit and combines the histories of both branches. Even if you haven't diverged, this results in a distinct commit that preserves the feature branch as a separate line of development. Now, a number of times you might want to maintain the feature branch because you're going to lose the branching feature. It looks almost just like it's at the same point as the main branch. And you can force the three-way merge, as we did on the right, by using the no FF flag. So when you do a merge, get merge -- no FF, and this option creates a merge commit even if the branches haven't diverged, allowing you to keep the feature branch distinct from the main branch. This approach is useful for preserving a clear record of feature branches, making it easier to track changes and understand the development history. So at this point, we haven't been bringing changes from main into feature. We've only been going from feature into main. And usually if there's a bug fix and something in main has updated, you'll want to apply them to your feature branch as well. Generally speaking, as you develop, it's a good practice to keep your feature branch up to date with the latest changes from main. And this means periodically merging changes from main into your feature branch to incorporate any new updates from other developers or fixes. In this approach, we perform repeated merges from main into feature, keeping the feature branch current with the main as main evolves. Then, when we are done, we go in the opposite direction and merge feature into main. However, when a feature takes a particularly long time to develop, requiring multiple merges from main, the feature branch can become cluttered with numerous merge commits. And this can go against the principle of maintaining a Git history that reads like a story, with each step clearly representing the development process. Too many merges make the feature branch harder to follow, reducing its readability and making it more difficult to understand the flow of our work. To avoid the clutter of repeated merge commits, the alternative to merging is to use rebasing. Rebasing integrates changes from the main branch into your feature branch without adding more merge commits, resulting in a cleaner linear history. And what happens is, with the command get rebase, Git temporarily lifts your feature branch commits and replays them onto your main branch. And this makes it appear as if the feature branch was developed from the latest state of main, keeping the history easier to read and follow. While rebasing provides a cleaner history, it should be done carefully, especially in collaborative projects, as it rewrites the commit history, potentially affecting others who might be working on the same branch. So you're often going to do multiple rebases to keep the feature up to date with main. And then at the very end, because the feature branch is up to date with main, you can do a fast forward merge and make it look linear. Now we're going to do a little breakdown on each step of the process just to take a look and review what we're doing. This could be a bug fix, a new feature, or any important change with a feature that needs to stay in sync with. So the first step, commit an update to main, which will advance the main pointer. Start by checking out the main branch and committing any updates or critical changes. Rebase the feature branch onto main. So we switch to the feature branch, check out feature, and use the rebase command to apply the feature branch changes on top of the latest main updates, keeping a linear history, incorporating all necessary updates. We will then repeat this for any further updates on main. So if more updates on main are made, we'll check out the main branch again and commit new changes. And finally, we'll merge the feature branch onto main to fully incorporate the changes. This keeps your feature branch aligned with main all the way up and the latest changes, and this minimizes the merge conflicts to help with stability. So if you were to merge everything from main all at once at the end, you're more likely to run into conflicts than if you do it piecewise as the main updates separate from the feature branch. This makes it easier to control and keep control of your development story. So this workflow has a few important benefits. Frequently rebasing feature on a main, we integrate changes gradually. This reduces the likelihood of large, difficult to resolve conflicts when it's finally time to merge them back together. Keeping your history clean, we rebase helps us avoid repeated merge commits, keeping the history linear. The commits will appear as if they were created on top of the latest main all along. So it doesn't look like you started the feature at the bottom. It looks like you started the feature when main was up to date. When the feature is complete, merging it back in will be simpler and less prone to conflicts, since the feature already contains all the latest updates. And this allows us to ensure that the feature is always in sync throughout its development and tells a much cleaner, nicer story. So I mentioned briefly earlier that you have to be careful when working with rebase on collaboration or collaborated branches, right? Branches that other people are working on. So there's a bit of a gotcha when multiple people are working on the same branch. Here we see a main and a feature branch in both remote and local repositories. So say we're developing on a local repository and someone else on our team is developing on the remote repository. Now I've labeled the nodes here for clarity, so we can see that the remote and local repositories share nodes up to E, but we've added an F node and an additional commit to our feature. So what happens when we do a merge? So rebasing is a powerful feature that lets you replay, and replay is the key word there. Replay commits from one branch to another. By rebasing, so if they rebase their feature on the main, it appears as if the changes were developed from the latest point, but in reality, they are redone, they are rehashed. It's because replays from that. It doesn't actually do a copy, so that when you look at the nodes, they are physically different nodes. So rebasing and remote branches don't mix very well, because when you rebase a branch and you're actually rewriting this commit history, Git never reuses the nodes. It only ever copies them. And this is now what we call a divergent history. So where the local history no longer matches the remote history. While the E node and the E2 node contain the same content, to Git, they are different. So if I attempt to push the rebased branch back onto the remote repository, when I push the local one on, Git will interpret this as a completely new set of commits rather than a simple update, because the commit hashes haven't changed. So now it doesn't know where to attach the F node to the E2 node. It only thinks it belongs to the E node. This issue arises because in Git, each commit has a unique hash. And when you rewrite the history or replay the history as we were doing, it gives it new hashes. And rebase, when you rebase a branch and then push it to the shared remote repository, you're effectively telling Git to replace the existing commits with new ones, even though they look the same. Anyone else who has pulled the original commits, as we have, and added a new node will encounter conflicts. And this can lead to confusion, merge conflicts, or lost work if you're not careful. So in essence, rebasing a shared branch can force collaborators to resync and reapply their changes on top of your rewritten history. It can create a complex and frustrating experience. Now, that's not to say that there aren't ways to deal with that, but you have to manually manage your merge and your rebase by hand. If you want to avoid that, so there's some common things when you're doing rebases, some best practices for merge and rebase. Instead of rebasing, you can always merge the main branch into your feature branch that we did. So this is if it's a small update, use merge. Rebase is best for large updates and continuous development. This preserves the history, and Git can automatically detect and handle conflicts. And this approach keeps the commit hashes intact, ensuring a smooth integration with other members' work. Use rebase on unshared branches. If it's a feature that you're working on alone and you haven't shared with a remote repository, you can rebase as much as you want. Rebasing before pushing your work is a good way to keep a clean and linear commit history, but only do it if you're certain that no one has pulled from or based their work from your branch. And of course, we wouldn't be mentioning rebase if it wasn't a useful tool. So there are times you're going to want to use it. But in this case, if you're using it with a remote branch or a remote repository, you need to coordinate with your team. If you really need to rebase the remote branch for some reason, significant refactoring or fixing a complex series of commits, communicate it with your team. Let everyone know that the branch history will change and give them instructions for how to reconcile their local branches with the new history. Typically, using git pull with the rebase flag to incorporate the updated branch will do so without duplicating the commits. In summary, while rebasing can keep your history clean in local development, applying this practice to remote branches that others might use is risky. Rebasing a remote branch rewrites the commit history, potentially causing confusion, conflicts, and at worst, lost work among collaborators. So instead, use merges for shared branches, like main. Main is typically your shared branch, and instead use rebase for local branches, your feature developments that you haven't shared yet. And following these best practices can ensure a smoother collaboration and avoid the pitfalls of rewriting your shared Git history. So we're going to move on to another tip here, and this is a bit of a shorter one, but it's an interesting one nonetheless. Empty commits in Git are commits with no changes to the content of a project, created intentionally for purposes like adding comments to the history, triggering continuous integration, continuous deployment workflows, or marking milestones. So if we attempt to make a commit without any actual files, Git won't perform the commit and instead just give you a little message that says there's nothing to commit. Working tree clean. If you have ever made a small change to a README to trigger a build or debug an integration, it's something I've done all the time until I discovered this handy Git command that lets you make an empty commit. So adding the allow empty flag to a commit, you can bypass the nothing to commit error, and this lets you trigger an automatic workflow or leave descriptive messages in your repository without modifying any files unnecessarily. It's also good for kicking off a continuous integration, continuous deployment CI/CD process without cluttering your history with minor edits. The Git history itself will show no actual changes except for the empty commit node. The next command we're going to do is we're going to go back to manipulating your branches with the cherry pick command. And that command allows you to apply specific commits from one branch onto another without merging the entire branch. And this is useful if you want to bring over only select changes without integrating all the work from the other branch. It's a bit more of a niche command than you might be used to. Unlike merge or rebase, they're used all the time. Cherry pick definitely is more of a specific situation kind of command. And what cherry pick does is it applies changes from one or more specific commits instead of merging the entire branches. Cherry pick will isolate the changes from the selected commits, so it's from this branch into your main, and creates new commits on the target branch, usually from one feature to another, from feature to main, preserving only those specific modifications so you can ignore the other nodes in that branch. And this is useful for selectively applying individual changes without bringing over the entire history of the branch. Cherry picking is similar to merge and rebase commands in that it incorporates changes from one branch to the other. However, instead of bringing over all the commits like merge does, it's only very individual specific commits. And then you can preserve the selected changes independently of the full branch history. So this is a much more fine-grained, fine-tuned approach to merging individual nodes over. Now, keep in mind, the caveat is you still have to deal with merge conflicts, in that if you edit to the same file on both branches, you're still going to have a conflict. And it's best used if the files are isolated in the commit nodes. So the more commits you do, the more often, if you keep them much more granular, it's a lot easier to cherry pick individual commits from one branch to the other. So let's demonstrate this. So we have 3 branches here. The yellow branch is a feature that my coworker is working on. The white is main, and green is a new branch that I'm working on. Yellow hasn't been merged in the main yet because they aren't quite done, but I still want certain changes from it. So if we take a look at the Git log, LG and alias for log. We first need to find the commits that we want to cherry pick. So we'll take these hashes. Now take note of the hashes that you want here. So these are the hash values on the left there, because we're going to be using those in order to identify what we need. I lost track of myself there. Sorry. In this case, we want the bug fix. We want to keep the bug fix one here. We don't necessarily need the logo. That sounds like something that's going to be specific to a branch. And we want the README, right? Those things important. So we write down the hashes. I've included them over on the right here for convenience, and that's what we're going to be using. So we switch to feature B, the green branch, and we're going to use the command git cherry pick with the commit hashes that we just looked at. So git cherry pick the two. You can use one or two, or you can as many nodes as you want, and they will pull those over. They will replay them into your new branch. So what it does when I run, it's going to individually take these over, and it's going to replay it as if I did this, each individual commit, and I just do them all over again. When we take a look at the git log again, we can see that the hash values in the feature B are different, or in feature A are different than they are in feature B, even though the commit messages and the contents are the same. And this is because, as I've mentioned before, Git doesn't actually ever copy nodes. It doesn't ever actually move nodes. It copies or replays nodes, creating new ones. The next command we're going to look at is squash. And a squash in itself is not a command so much as it's an option when using rebase. Unlike other Git commands that add, move, or modify nodes, squash does the opposite. It reduces the number of nodes in a branch. Now, this might seem counterintuitive, but there are good reasons for doing so. Squashing allows you to combine multiple small incremental changes into a single cohesive one, creating a cleaner, more understandable commit history. This is especially useful in projects that have a lot of minor debugging commits or fixes and consolidates them all into one meaningful change. And because we often emphasize commit early, commit often, this can lead to unnecessarily cluttered comments, especially during debugging or learning or experimentation. Squashing lets you clean up these spurious commits, rewriting your history to present a more cohesive development narrative. So you do this kind of thing before you want to merge back into main, just to make it easier to read. So ultimately, this improves your readability, and it transforms your Git repository into a more organized log of your development process. And it's another step towards using Git as a comprehensive DevOps tool. So a quick review using merge. Here we have a feature branch that has been merged into main using the default three-way strategy. After merging, we can take note that the history of the main branch is integrated with the features branch commits to keep its own linear history, and the feature branch still exists. However, this is a three-way merge. You would delete the feature branch yourself using the branch -d flag in order to remove it. But alternately, so this this slide is going to outline an ugly scenario where the commit history has become cluttered due to multiple parallel commits without consolidation. If we look at the Git log to see what we've done, we can see a common scenario, particularly for people who are working independently and they aren't as motivated or pressured to keep their Git history clean and tidy. So we've got our added main, our initial node, added a header file, added a body file, a check-in for the night. And that's something that I myself am guilty of, is that I'll use GitHub as a code backup, just in case your computer blows up overnight. You don't want to lose all your good code. So I'll do a check-in and push it to remote repository, even though I might be in the middle of an update or something might not be quite finished. So finally, I get everything done. We finish feature, and we've got the feature complete. Now we're ready to merge it back into main, but here we've got multiple commits, and we want a way to reduce this to make it look cleaner and describe what we did a bit better. So we're going to use squash. So here's a typical repository setup with a main branch and a feature branch containing multiple incremental commits. And then we squash it. So by using squash, we reduce these multiple nodes into a single commit in the feature branch. And this doesn't delete the feature branch pointer. Instead, it consolidates the commits, making the branch history cleaner and easier to follow. Squashing simply combines all the changes into one, but it's up to us to perform the final merge, as squash doesn't merge in automatically. So in this example, we used a three-way merge, but you could just as easily use a fast-forward merge because we've squashed everything into one node. It depends on your desired history structure. So to achieve the squashing effect, we'll use what's known as interactive rebase on a repository. And what interactive rebase is it's using the rebase command, but it's going to open up an editor for us to instruct it how to work. So the goal here is to take multiple commits in the feature branch and reduce them to one. And then we're going to integrate those consolidated changes back into main, as we've seen in previous examples. So we use get rebase minus I for interactive, and then head tilde 4. So we specify the last 4 commits. So head tilde 4 means this is the head node, feature is checked out, 1, 2, 3, 4. And that's as we want to rebase from this node. Now you could just as easily add in a hash or some kind of tag value as well, but I find that using a reference from the head node is a bit more intuitive in that you say head tilde 4 will just give you the 4 nodes, the top 4 nodes of the branch that you want. So interactive rebase, it's going to open up. It allows you to combine and rearrange these commits, tell a clear, cohesive story. And it's going to do this by opening up an editor. It's going whatever default editor you have. I typically use Vim, and you'll see a list of commits that you can reorder or modify. So we've done the last 4, so these 4 are in there. Now there's main commands. There's a number of commands, and this is abbreviated even from what's available so that it fits on my slide. But rebase, interactive rebase is quite a powerful tool that does a number of things. The ones we're going to focus on here are pick, which is to use a specific commit. Squash, which is to meld the commit into the previous, so that they are in order. So if you squash one, it will meld it into the last one that you picked, going from top to bottom. Of course, there's other commits available, like reword if you want to edit a commit message, drop if you want to remove a commit entirely, but we're just going to focus on pick and squash. Now, as we know, each commit is identified by a unique hash, which you see listed next to each line. So you've got the command, the hash, and the message, the commit message. If you want to pick a commit, you would put pick beside it. You can also just put P, but pick is a bit clearer. And if you want to squash the commit, you will replace that pick in your editor with the word squash. So those are found right there. You must leave at least one pick because that's what Git will be squashing into, usually the one on the top. So here we've done that. We've changed the picks to squash. We've left the rest of the line as it was. When we exit our editor, in this case Vim, we'll do :WQ. It's going to open up a second editor. And here we'll condense our previous commit messages into a single clear summary. You can rewrite the messages however you like the best. This is all going to go into one node. And remember that any line prefixed by a hash sign, a pound sign, will be ignored. So you can make sure that your actual commit message doesn't start with a hash, and then simply write the message on the lines without hash symbols to include them in the commit. In this case, we simply condensed and kept the previous messages that we wanted, and that's what will be written to the node. If you exit the editor again, right quit, it's now going to condense those nodes together and rewrite your feature branch. From here, it's up to us to merge the consolidated branch back into main. So we will merge it ourselves. Now, if you've made a mistake, if you've made an oopsie During your interactive rebase, don't worry, Git has you covered. If you have somehow gotten stuck, you can use git rebase with the abort flag, and this will revert you back to your state before the rebase. But more often than not, you've maybe completed the rebase and you've changed your mind. You still have some recourse. And that brings us to reflog. Not reflog, reflog. With reflog, you are truly getting into an atomic level of Git, and it allows you to track every change in your repository at a granular level. Reflog is kind of like Git's memory. It's Git's storage, and it logs every update that has ever been made to head. So you can see exactly where your branches have been, where you've made mistakes, reset branches, force push changes. Anytime you create a new node in Git, the head pointer gets pointed to it. And it's, I don't even know if it is possible to create a node without having the head pointer point at it. So it's a pretty good record of what you've done. So we'll get reflog, like says, making a tracking history for all the actions performed in your repository, even if they aren't part of the regular commit, even if they're not visible on your tree anymore, they're still there. So it keeps a record of the head pointer, allowing you to retrieve the lost commits, revisit previous dates, and undo operations like git reset or git checkout. And it can be a lifesaver when troubleshooting or recovering from mistakes. So if we take a look, these updates are logged with reflog. So the changes are, we have seen what we're currently at, right? The head pointer currently points to master and feature. Got a message, and we've also got a little shortcut command, because you can check out any entry you find by putting in the hash code, or you can use its reflog identifier, which is this head at and the number 0, 1, 2, so on. And the number in the curly braces represents the position in the reflog history, pointing with head 0 pointing to the most recent entry. And this shorthand makes it easier to navigate and restore specific points in your Git history. So you can go back 1, 2, so on and so forth, specific number. Now, if you take a look here, and there are nodes in here that we didn't specifically do. So there's a rebase node that we didn't make, but that was created because we did a rebase command. You check out the head, it moves to a different node there. Of course, our initial commit has a node, and so on and so forth. Even at sometimes, so this checkout and the initial commit both have the same hash value, because while the head technically moved, it didn't actually point to a different commit. Just interesting little points there. So to actually, when you want to, so we've got to commit to AC, right? We're going to want to check out, say we want to update feature pi, we want to go back to that point in our history. You will use simply check out the hash code, and they'll tell you you're switching to that. And Git responds by telling you you're now in a detached head state. And you've probably seen detached head at other times. And that just means that your head is now pointing to a commit that is no longer on the top of a branch, right? And in this state, you can look around, make experimental changes, and even create new commits. However, any commits that you make here won't be tied to a branch. So if you switch back to a branch later, these commits will be left behind and it won't affect any of your branches. If you want to keep changes you make here, Git suggests creating a new branch. So down here with git switch -c, which is a very similar command to our previous one, git checkout -b, where it will switch to a new branch with a new branch name with whatever node you currently have checked out. And then you can go back to your previous branch with git switch dash, which tells you that finally Git also tells you that you can turn off this device by setting a config variable. I like to leave these things on because you don't use them very often, so it's good to know how you're good to remind you on how the commands work. So thank you, and I'll now invite you to ask any questions that you like.